All right, everyone. Thank you for coming to our webinar this afternoon on the future of fresh laser perforating and modified atmospheric packaging. It will be a 20-minute presentation given by Dr. Nazir Mir and Chris McCune. We'll have 15-minute question and answer afterwards. So if you would like to submit any questions while we're going, please just hit that Q&A button at the bottom, and we will answer those questions at the end. Just for you guys' knowledge, the session will be recorded, and a recording of the presentation will be sent out to all of the registrants either later this week or early next week for your viewing. Chris McCune is our Managing Director of Packaging here at Preco. He has an extensive background that combines technical knowledge with a strong customer-centric approach, enabling him to deliver tailored solutions and meet complex customer solutions. Dr. Nazir Mir is a post-harvest scientist with over 30 years of experience in the perishable food industry. He specializes in microperforated film technologies and has led the development, validation, and commercialization of shelf life extension solutions in partnership with the PhD food scientists at Rutgers University. So I will hand it over to Dr. Mir and he can continue.
Thanks, Quinn. First of all, good afternoon, everyone. And I would like to thank Preco for inviting me and giving me an opportunity to introduce the packaging concepts that we work at Rutgers University. We are reasonably, well engaged in developing packaging solutions for perishable food industry. That includes, some of them include microperforations. So when you are designing a food packaging system, you need to first have a good understanding of the food that you are going to preserve and use packaging as a means to preserve or as a means to deliver to the final consumers. In this country, there are food safety laws which require that if you deliver a food to a consumer, that must be safe. So sometimes by design, we create a package that gives us some quality indicators. So the point I'm trying to make is when you are going to go to a retail store and if you see a package and you see the quality is not as good, you will make a decision not to buy it because you might think or the decision that you will take, you will relate your decision to the quality, and the quality being poor, you can clearly see it. And so, in other words, you wouldn't get in a food safety type issue. On the contrary, sometimes there are certain foods and you design a package that seems to be optimal for preserving quality, but somehow, the external changes don't appear, and a consumer can inadvertently consume, and if there's a food safety issue, they may fall sick. So therefore, from a food scientist standpoint, designing packaging is critical, primary being to preserve food or to preserve the food quality, but at the same time making sure that the food consumers consume is safe to consume. A typical example I will give you is, for instance, a banana package. We don't grow banana in this country. We rely on our neighboring countries, and there are major companies like Dole, Chiquita, Del Monte. They bring banana to this country in a green state. And if you develop a technology where we are, which would be the primary focus of today's talk, is called modified atmosphere packaging. As you lower the oxygen in the package, so you also preserve the green color, but that green color is no indication of what is happening inside what we call the pulp of the banana. So many times the fruit that looks green may not be good from the quality standpoint. So we're going to go into detail in the coming slides. The point I'm trying to make is when you design a package, you need to work with a processor, with a guy who's going to pack it, a co-packer, and understand the intrinsic characteristics of the food, because there are certain foods that that have certain, you know, characteristics that degrade too quickly. So there is not a one solution fits all. That approach doesn't work, especially for the perishable food industry. And then you need to also have a good understanding of the supply chain or the environment while in the package or the food put in a package or a packaged food is subjected to, what we call as extrinsic factors. So an example of an extrinsic factor would be if the package, sits at a higher temperature for some, time, microbial growth can take place, the respiration rate can increase, so that can make the package go anaerobic, or if there are some pathogenic microbes that might proliferate and end up in a food, safety issue. So those are type of things that, as you design, we try to avoid. Packaging primarily used to be a means of containment, but now concepts have evolved. It is now a major means of communicating, with the customer. So you have these printing technologies wherein you can put your, a lot of things on the nutritional labels. So you're basically communicating with the customer and trying to grow sales. So it has become not only a means of containment, you protect the food, it's a means of convenience as well. So a lot of functions are delivered now through packaging. As far as perishable foods are concerned, there are a number of technologies that we generally use. We use controlled atmosphere packaging for the bulk produce that we move from in container loads. You have certain technologies that we know, uh, certain products are very sensitive to ethylene, and so you have either ethylene absorption technologies or ethylene action modifying technologies. So while in addition to package, they help you extend the shelf life. Um, you have antimicrobial packaging, and you also now use packaging to cook. Like, so there is a lot of market called what we call steam cooking. In all these technologies, if you are using microperforations, the microperforations are used to basically, uh, control the respiration of the product. And so we're going to talk about just modified atmosphere packaging in this presentation, but there are a number of technologies. If you guys have any questions, please feel free to reach out to us. Uh, I think my contact, maybe I can give you my contact. You can directly reach out to me or reach out through Preco. Is no issue at all. So we are going to talk today because these guys are, their focus would be to offer microperforation systems. So we are going to put quite a bit of our time or of the presentation on use of microperforated films for extending the shelf life of perishable foods. So as a food supplier, if you need to be in a national distribution system, generally required shelf life for most products is 17 days. So unless there are some intrinsic factors that push you as a co-packer to have less shelf life, so there is not much a packaging can do. Um, if there are other factors that are controlled, then microperforations, they help to extend the gas transmission rate of flexible food packaging films. Uh, there are a number of applications that you go to any retail store, you will see is a huge section is dedicated to the salad bags, A lot of cut products are put in a package. So if you design the package properly, it certainly does extend the shelf life. And that is why there is a market, and that is why people are still interested in either putting a lot of efforts in film formulations. You can have two approaches basically. We can have a novel chemistry approach wherein you can go all the way down to barrier packaging to OTR specific packaging and reach to a cutoff of around 800 cc's per 100 square inches per day. But if you need to go beyond that, you have to use microperforations as a means to uh, improve the gas transmission rate of the films. So if you look here, when you put a product in a package, so what we have shown here, there are little, those dots that we call, it is then basically a perforation, whether a micro perforation or a macro perforation, but it helps the gas transmission. So when products in a package respire, what they do is they consume oxygen, and in exchange they produce CO2. So an optimal package has to let the CO2 come out, the oxygen has to come in and allow the product to respire, and that respiration has to take place at maybe 1/10 of the normal rate of respiration. So you have to let the product breathe, but that breathing should not be in a judicious manner such that whatever assimilates or energy reserves this product has created while it was growing, the rate of respiration, if it is higher, will burn it down too quickly, and therefore the product shelf life would be quick. So the one way of scientifically increasing shelf life is to gain control on the rate of respiration. You control it to a point that it doesn't suffocate, because if it suffocates, it will die too quickly. Like example is, we as human beings can be without oxygen for maybe 45 seconds. So if we stop breathing, we will die after 45 seconds. The fresh produce products do pretty much the same way. It is only it takes longer time for them to die. They don't die that quickly, maybe in days, but they do die. So therefore, the perforated film membrane that you are going to use has to match exactly the respiration to a point that it controls it but does not let it die. So there is a lot of mathematical modeling, many years of experience in this field, product specific respiration rates. Then you have to analyze the co-packers processing techniques, the growing factors can have an impact on the rate of respiration. For instance, I work very closely with the fresh produce industry. Most of the fresh produce salad market is the growing area happens in Salinas Valley, but they move for certain seasons as the temperatures spike, they go to Yuma. So the products grown in Yuma, Arizona, are not the same that grow in Salinas Valley. So therefore, from time to time, you may have to make permeability adjustments or OTR adjustments. So therefore, all major companies have R&D guys, and if a packaging company has an R&D guy on their side, I think the communication becomes a lot easier, because at the end of the day, we're all elements of a supply chain, and our goal is to make sure that we service the industry and we, under all circumstances, provide a safe food to our consumers. If sometimes there are safety issues from time to time, I had some of the students do a search in last 5 years, and on an average, we report 20 recalls a year. And as you know, recalls are very expensive, and some businesses can go under. So therefore, it is critical that a package is optimized for shelf life, and under all circumstances, is safe. The food in a package is safe for consumption. So this is basically the principle of modified atmosphere packaging. You start with uh, an environment like we have around 21% oxygen in the environment. You create a membrane, whether through film chemistry or you, depending on the rate of respiration, you may need microperforations. The oxygen, you know, as breathing starts, they start consuming oxygen. It comes to a steady state level, and that is many mathematical modelers will model a package using a steady state rates of respiration. And this is a snapshot of some of the products. Asparagus has the highest rate of respiration. So therefore, the point we're trying to make through this slide is every product is different, has a different rate of respiration. And again, here we're using only respiration as a you know point to be controlled, but there are other variables that can have an impact. Some foods have microbial loads. Microbial physiology works differently than the plant physiology. So you need to understand fully those interactions and then design a package. But certainly if you are using microperforations only tailor the oxygen and CO2 transport through a package. Um, so in this slide, what we are trying to show is normally, so if you focus on the line that is below the non-perforated, the red part, normally the permeability of CO2 through a package, through a polymer, is around 4 times of oxygen. So if you have 20% oxygen in a package and you are using the packaged product to consume all the oxygen, so 20% what was in the entire internal space got converted to 20% of CO2 in the internal atmosphere of the package. But since the polymer has 4 times capability to remove CO2 because it is more permeable, 4 times more permeable, the net accumulation of CO2 in a package will only be 5%. That means the product is already anaerobic. So that means it's like this zero. And and that is not something we want to do. We always in a package, we need to have at least oxygen in like 0.5% or higher. So otherwise the product below zero point 0.5 will go anaerobic. There is another indicator, what we call as a fermentation potential or a respiratory quotient. I didn't show in this slide because didn't know the audience how interested and what their background would be. But as a rule of thumb, you can you know assume that as the package goes from an aerobic respiration to an anaerobic respiration, like we're just fermenting, it is developing off odors. The product will start smelling, especially product like broccoli.
Sorry, everybody, for the technical difficulties, but it is one thing that I've learned working with Nazir, and a lot of times when we have an end customer that has a specific produce that's going in a specific size package, there is more science to it than at least I was aware as far as looking at the total, not only just the package size, the product inside of it, and where it's going, but you got to look at the transport of that material, of that package. There's a number of factors, and like he showed, the CO2 to oxygen transfer rate is different for different produce. So that's where what we call a recipe, or the number of perforations required in a package, is basically tested to optimize the shelf life of that particular package and that particular produce. And as Quinn, if you go back to a couple of slides where it shows kind of a difference of, this many days and how many days before the produce starts to rot, basically in a package. does show a big difference. There's some good comparisons between day 14, with micro perforation where you've got proper transfer compared to improper amount of transfer. And in the same number of days, you can see how the material starts to degrade, the produce starts to degrade in the package. So that's what all the effort is about, is obviously trying to optimize for that end customer what the maximum shelf life that you can. It's showing just basically examples. Like on the left here, you've got, one that is utilizing proper recipe or getting oxygen transfer compared to one that's not properly. And it's pretty easy to see the results and within that 21 days that Nazir talked about. Just some more examples of modified atmosphere. And so what we do at Preco, obviously, is we offer solutions. How do you get that micro perforation into the package? And we utilize, a couple of different systems. These represent two of our new models, our Beeline web direction and our Firefly cross web. Both of these systems typically are connected to a slitter line, but it gives you the ability to do micro perforation on your wide web across however many impressions that you have to be able to do that recipe, the optimum recipe for that particular package for your customer. This shows in our web direction for our Beeline, we've got a Preco proprietary. We've designed this over the many years that we've done film perforation. It's called our beam compression head. And it, our standard spec, it depends on material, it depends on the film structure, but typically with this, we're able to get somewhere between 75 to 125 micron holes, perforations, good round perforations at speed, at slitter speed. Ah, Nazir, you made it back.
Yes, I apologize. We had heavy floods in the area yesterday, so this power went for some time.
Oh, that's unfortunate.
Yeah.
But I'm gonna let me finish talking about the equipment and then let's go back to where you were in the presentation, if that's all right.
Yeah, no issues. Yeah.
Yeah. So we've got our beam compression head to be able to do the micro perforation and web direction. And then with our cross web system, we've got a new product that we're excited about. This is actually, it's called our Stinger head that you can add to our Firefly cross web system. And it gives you the ability to do micro perforations with a galvo system, which that typically is not, it's not something common for most solution providers, because what the issue is that the laser beam coming out of a galvo is a large diameter beam. So you obviously can't do small holes with a large beam diameter. And we've come up with a way to add these heads, right? Basically attach it to the galvo, and we can get that beam size down to where we can do, around 100 micron micro perforation in web direction. So that's actually something we're excited about. It's a new product for us, and it gives you the ability with a galvo system to do that micro perforation. This we're just talking about. This is how Preco categorizes perforations. There's sub 65 micron, which we call nano perforations, and this is a proprietary. We've developed a proprietary technique to be able to do the sub 65 microns in films. It's only really available at our Somerset facility. It's a very specific setup to be able to perform that small of holes, but it can be done as toll work in our facility. And then we call the micro perforations at 65 to 200 micron, which micron holes, which can be done with our standard beam compression heads and or the stinger head that I just talked about. And then if you get above 200 micron, a macro perforation, that can be done in web direction with lens adapter. We can actually, in essence, expand that beam to get a bigger hole diameter out of our web direction, or with a galvo, the 200 plus, we're just doing it with that large laser beam diameter, and or we can also, do it with geometry if it's even a larger hole. We can have the laser cut that round geometry to a larger hole. So that gives you just a synopsis, a quick shot of our perforating capabilities, and I'll turn it back over to Nazir. He can talk about the technical, scientific side of creating that. So again, we apologize, but Nazir, I'll let you take it back over.
So on the upper side of this, what we are showing here is if you are using micro perforated packaging as a means of gas transport, you can certainly go up to, hypothetically up to 20% CO2 accumulation, which would be very difficult to achieve under commercial conditions. But a lot of products that benefit from high levels of CO2 within a package, you can certainly use microperforated film and get CO2s in the range of 10 to maybe 15%, ideally. So these are some of the examples that we have. Cilantro is shown here. So if you have no perforations in a package, in this case that we were working with a customer, and the product would go bad, in few days' time. Not their fault. It's just, they probably didn't know much about the polymers that they were using. And, sometimes some of these products would make ethylene. And if this ethylene stays within a package, and that will turn the leaves go black. Classical example is basil leaves, and basil leaves are really high value. So you need to sometimes an optimized package doesn't delivers a great value. If you have an optimized map, in this case, we were able to work with this customer. They will consistently have around 14 to 16 days shelf life on these products. But if you do not have, you have too many perforations, sometimes people believe that, you can put any number of perforations. We would end up having a product, becoming dehydrated or have excessive senescence. That happens with some leafy products. One of the things when we design a package, we based on our understanding or the scientist that you will have on board, on his understanding or her understanding, we will do the best. But then you have to do product development is different than what you call a packaging design. So if you design a package, it needs to be tested under robust conditions. So sometimes you artificially create conditions, you stress the package. In this case, like onions also have a food safety concern. You may have heard multiple times, in the prior world, the Taco Bell issues. And in this case, we designed a protocol wherein we would stress up to 79 degree F and design a package that would withstand those robust conditions. So when it went through a supply chain, which normally I said before is around 17 days, then it would withstand and offer the quality that the supply chain was looking for. Yeah, here again on the left side is a microperforation, just for comparison. Macroperforation, same time, here is 14 days or 21 days. Certain products, ideally you would like to have 17 days, but some can be extended even further. We have worked with the broccoli export, the people who were trying to export to send the broccoli to Japan, and our shelf life would be 30 days in that case. Let us take questions, and yeah.
Yeah, so I do have a couple questions already. So, the first one I have is how do you calculate the optimal number of perforations for each fruit or vegetable?
Yeah, so probably is this is a question for me. So the way you work is you need to have a reasonably good understanding of the process. It means the growing conditions, the product, the variety, the how you do the cutting, whether it's a fresh cut product. And so you come up with a what you believe mathematically would be the accurate. But then you need what we call product development. You need to work with a supplier. I wouldn't jump to just package design and you offer a solution. As I said before, food safety is critical. Under no circumstances do we want to create conditions that would compromise safety. Uh, and so therefore it is going to be a process wherein everyone plays their part and it is a collective effort that's going to lead to a successful product.
Perfect. The next question is, how do you figure out what the pattern is and where the pattern will go on the package?
Yeah, that is reasonably easier. Once you have selected what you need someone who, what we call, can integrate the process. As a manufacturer, they would make a roll stock, and that roll stock needs to be used at a packer's facility to package a food. So you need to see how that package works. And then you need to understand whether that co-packer is going to use a label or is already printed roll stock. Like we have labels in a lot of leading film applications. Then we need to understand IMAR because the package that you create or the roll stock that you create needs to talk with the processing equipment that you use at the co-packers level. So that if you create a perforation pattern that's not blocked by a label or it is not at the bottom of the package where the product weight itself is blocking the flow through the perforations. So it all comes through having someone on your team who understands the equipment, who understands the packaging, converting, and of course would have some, science background or food science background.
Next question is, can you speak to the quality control methods that are being used to confirm the overall per package ventilation that is being achieved while in production?
So if you are talking of quality control procedure or the production procedures, right? So someone needs to have a good understanding of co-packer processes. A packaging company, if you try to offer a product, if we are again asking about the targeting the fresh produce industry, you could see like one co-packer has many SKUs in the market. So you have so many labels. Each label has different weights, different products. So you're talking of hundreds of SKUs on a daily basis. So therefore, without having a proper understanding of the co-packer's process, I think it would be hard to kind of predict that from a packaging supplier standpoint.
On the equipment side, if that question's referencing, what we can do technically on the equipment, there are methods. For example, we've got a closed loop control system built into our laser that confirms whether the laser pulsed. And so you'll get an alarm if you're not getting a pulse, therefore not getting a perforation. Also, we can integrate different camera systems to also ensure that there was a perforation in that film. And there's different options available for technology on the on the mechanical side, the equipment side of how to do quality control. So I'm not, but they're kind of answered it two ways there. Nazir on the end user side, and I was answering on the equipment side.
Sure. And then on top of that, Chris, uh, whatever you do, mistakes happen. And whatever you do, you have issues from time to time. your goal has always to minimize those issues. Not eliminating them completely is hard. So you put what we call quality control procedures in place. So even if your system says it pulsed, for a scientist like me, doesn't mean it made a perf. Even if you say it made a perf, for me, doesn't mean it made the right perf I wanted it to make, right? So these are all questions and it comes with experience. So what we do is, so if there is a packaging company or a converter, he will have, or they will have a quality control procedure in place. So you will maintain retains, because that is a requirement. If some issue comes, your retains should say or validate that the film that you supplied was within specs or was not within specs, right? So that's why it is not just one process fixes it all. You need to have a reasonably good understanding from the packaging, where packaging is made, downstream, where perps or polymers are extruded. Everywhere quality control is essential.
Chris, there's one that just came in that said, can the Preco laser units be incorporated into our existing press?
Into a printing press, I'm gonna say that's what they're asking. So typically our laser systems, it depends on the whole. For example, if we're just talking about micro perforation, speed is dictated by the hole to hole distance, because we've got a limitation on how fast we can pulse the laser to create that. An example would be, I mean, if you had an inch hole to hole distance, we could run up to 2,500 feet per minute. And then you can kind of
Before you
scale
finish,
down from
Chris,
there.
he
Yep.
did clarify into their Preco hydraulic press.
Oh, okay. That's a whole different subject. So that would really, one we'd probably want to take offline, just to see, clearer line of sight, just see what kind, what the custom application would be for that. So if you wouldn't mind, please get a hold of us. We could take that one offline.
What is the transmission rate of one hole perforation 100 micron?
Nazir, do you want? I don't know if you've got an
I don't
average.
know the answer.
I know it's that's a little bit tough to answer, but I'll let you take a shot at it.
Yeah, no, it's not as simple. Like,
Yeah.
it all depends on the thickness of the film, the polymer, and there are a lot of variables in it. So I maybe want to take it offline to help if I can. But it's not as straightforward. You make one hole, you have this much OTR. That doesn't work.
Let's see. What is the typical size range of perforations in food packaging?
What we've seen, what typically gets called for is that, and that's why we designed that head to be. I'd say the most typical is right around 100 micron. But that 75 to 125 micron takes care of most of food packaging specs that we run across. There's always some that go to the lower side or higher side, depending on what the package purpose is. But that's what we see most often, is around that 100 micron.
And we just have one more, unless anybody else has one. Where in the converting process are the perforations typically done in the film? And we kind of talked about that one, didn't we?
Yeah, most of the time we see it on the slitter line. We're typically integrating our laser system to a slitter. After it's been printed in wide web, they're unrolling the wide web to slit down to the particular sizes for the bags or pouches. And typically, while it's still in the wide web, we're performing the perforation on the number of impressions across the web. Then it goes to the slitter and it's cut down to the size required for the customer.
And then last one, again, I say that a lot, but does this require a special laser to perform the perforations in thin film?
Typically, as far as special, lasers, there's a lot of different types of lasers out there. The most typical laser used for, PE, PET film, which is most common for food packaging, is typically a CO2 laser, but the CO2 even comes with a lot of variations. You've got different wavelengths. And so, again, it's important to know what the film structures are, what the thicknesses are, and what basically what the spec is, and we make sure and spec out the right laser for the right job. But most of the time we're using, a 10-2 or a 10-6 CO2 laser is the most common.
Excellent. Well, that's all I have for questions. So thank you everyone for coming. Thank you, Nazir, and thank you, Chris.